The equation you see in the background here is called the Planck-Einstein relation, and it says that the energy of a particle of light equals the constant h, Planck's constant, times the frequency. It's one of the great equations of modern physics, and I wanted to explain why it's important in your life. Basically, around the turn of the 20th century, Max Planck had realized that energy appears to come in discrete values, kind of like how we can make change for 1 cent, 2 cent, 3 cent, 4 cent, but we can't make change for 0.17 cents. That there seems to be a minimum allowed value of energy. And Einstein took this as he was looking at light, and he used it with the idea that light can be thought of as a wave, and we understand what frequency means in a wave. It has to do with the number of cycles per second. But it can also be thought of a particle. And each of those particles of light that falls on something carries energy. And it turns out that the energy each of them carries depends on the frequency. Higher frequency light, as we move towards the purple end of the rainbow, carries more energy. So this demonstrator here was put together by Arbor Scientific, and it's got some LEDs of different colors. On the far right is an infrared one, which I can't see, but you'll be able to see a little bit through this iPad camera. Then comes red, then comes green, then comes blue. We know red has the lowest frequency, blue has a higher frequency, and according to this equation, that means the energy per charge needed to light up red is less than the energy per charge needed to light up blue. So I have this all hooked up to one of those hand crank generators. I don't think you can, oh, there we go. It's the kind we had when we were talking about electricity and magnetism. And as I spin it, you'll hear it go faster and faster. So I'm going to start out really slowly. And you can see we get flashes in the IR one and flashes in the red one. The thing's not putting out much voltage, not much energy per charge when I spin slowly. But if I increase it, I'll have more voltage, more energy per charge. And we should see green start to light up. There we go. But notice I have to go faster to make that happen. And if I start going really fast, a lot of energy per charge, we start having blue light up. So this has practical consequences. As the frequency increases, the energy each particle of light is carrying increases. And that means at some point, each particle of light could be carrying a dangerous amount of energy, enough energy to, say, blast apart a chemical bond. And that happens above the frequencies of light we can see, above visible. So if we look at the spectrum on top of this piece of paper, the lowest frequency lights are radio waves, then microwaves, then infrared, then visible. You can carry a lot of energy with each of those, but you do it by sending out lots and lots and lots and lots and lots of particles of light. But once you get above visible, each particle of light can be a problem because it could carry enough energy to blow apart a chemical bond. And we call this ionizing radiation. If it's a chemical bond in a dye or in ink or in film, we call this fading. But if it's a chemical bond in your body, this could be a real problem. It could give you sunburns. Or worse, if it's something that has to do with the cell's reproduction system, it could damage that and could create a cell with the wrong DNA, a cell that's not possible to stop its growth, which is what we would call cancer. So when you get above visible light, these other types of light are dangerous, and they have to be carefully controlled. Now we can control UV light by wearing clothing that covers up more of our skin, because the sun does give off quite a bit of UV light. We really need to stay away from tanning salons because it's basically giving us UV light deliberately, which is highly increasing the risk of cancer. We need to limit X-rays. That's why you have to wear those lead smocks when you have an X-ray taken, so that parts of your body that don't need to have the X-rays going through them don't. And they're particularly worried about your ovaries or your testicles because they don't want damage in the DNA that could be passed on to the next generation of people. And this is why we have to shield nuclear reactors so well to protect us from gamma rays. So this kind of out there equation, it has really serious consequences. The higher the frequency of light, the more energy each particle of light carries. And that means those higher frequency particles of light need to be treated with respect.